peoples, and all of their ancestors and descendants, past, present, and future. Today, the UCR campus is home to many Indigenous peoples from all over the world, including UCR faculty, students, and staff, and we are grateful to have the opportunity to live and work on these homelands.
Well, good evening and welcome to the UC Riverside Science Lecture Series. My name is Peter Atkinson and I am the Interim Dean for the College of Natural and Agricultural Sciences, or CNAS for short. Today's Science Lecture Series is part of a full day of events that we've been holding on campus. They're called the Frontiers of Physics, and it's a celebration honouring Nobel Laureate, Distinguished Professor and Endowed Term Chair for Teaching, Research and Service, Barish, for being awarded the 2023 National Medal of Science by President Biden in the White House. The National Medal of Science is the highest honour bestowed by the United States government to individuals in science and engineering who have made significant contributions to their respective fields. Dr. Barish was awarded the National Medal of Science for his exemplary service to science, including teaching groundbreaking research on subatomic particles, the discovery of gravitational waves, which were predicted by Einstein's theory of relativity more than 100 years ago, and many other achievements in science through his career. We are honoured to have Barry speak to us tonight in our public lecture series, and I'm personally looking very much forward to it. But before we begin, I'd like to invite Chancellor Kim Wilcox up to the podium to say a few words.
Thanks, Peter. Great to have everybody here. On the way over, I found myself thinking about things you can't see. Now, of course, there's little things you can't see, like bacteria and molecules and germs and cells and things. But there are big, vast things you can't see as well. And best example of that is a black hole, where all the light gets sucked in, you just can't see it. But think for a minute about how we all know and believe that there is such a thing as a black hole, even though no one's ever seen it. And most of us will never get close enough to ever experience it in some sense. But even the small children in the room here in grade school know there's a black hole. How did that happen? It happened because a handful of scientists, now I know some physicists in the room are saying, wait a minute, it wasn't a handful, it was hundreds of people over decades. In a world of 8 billion people, that's a handful. A handful of scientists first conceived the notion of a black hole, then confirmed the notion of a black hole, and are now exploring the behaviors and consequences of black holes. That's what science can do. Go to places we can't see, or some of us can't even imagine, and explain it in a way that we all trust it to be true and take it for real. That's what Dr. Barish did. He not only talked about black holes, but two of them bang together and they make waves. Oh my goodness. Think for a minute. In this room, there are waves all around us. Everybody's got a cell phone. Electromagnetic waves feeding information to your cell phone. Somehow, magically, we all get the right pictures in our Instagram account, even in a room like this. There are waves. But to imagine a wave created by two things you can't see, it hurts my brain. That happens because of great scientists, but also great scientists who can tell the story. Dr. Barish created a coalition of scientists around LIGO, the sensory system that discovered or confirmed the gravitational waves, comprised of scientists from 19 different countries, hundreds of institutions together. It was a collaboration in science, but also a collaboration in sharing information. We're very, very proud of Dr. Barish's connections and successes, but we're really delighted with him as a colleague. Professors are people who profess. They have to know a lot and they share a lot. Barry does both of those to the utmost degree. He's the ultimate, consummate colleague. He knows his students, he knows his colleagues, he contributes to the betterment of the entire campus. On campus, we don't talk about Laureate Barish, we don't talk about Distinguished Professor Barish, we don't talk about National Science Winner Barish. Everybody calls him Barry. That's how great science gets distributed to many minds, having a person with a great mind who's engaged with so many people in such a deep way. And I'm just so proud of Barry and his accomplishments, but so grateful to all of you to come and be part of this celebration that means so much to all of our, the entire UCR family. So thanks so much for being here.
Okay, thank you, Chancellor Wilcox. So I'd like to now invite to the podium the Chair of Physics and Astronomy, Professor Shanwen Tsai, who will do the following introductions. Shanwen.
Well, on behalf of the Department of Physics and Astronomy, I also like to welcome you. It's a great honor for me to be making the introduction today. So Professor Barry Barish joined our department in 2018, and we are very, very fortunate and grateful for his service, his vision, his inspiration, and his dedication in creating a center for cosmology here in our department. To introduce him today, I will call another special colleague of mine. That's Professor Ken Barish. So, yes, Professor Barry Barish's son is also a faculty here. Ken is a nuclear physicist. He has been the deputy spokesperson for the STAR collaboration for the relativistic heavy ion collider at the Brookhaven National Lab. He is currently involved in the electron-ion collider, which is essentially is going to be the best microscope in the world that will look inside the structure of the nucleus of the atom. Ken was also a former chair of the department. So please, let's welcome Ken to introduce his dad.
Thanks, Shanwen, and especially for your leadership in our department. So what I'm not going to do, I'm supposed to introduce him. I'm not going to go through his CV, which actually is really dense. Any one of these, if any of us had any one of these, it would make our careers. It's also not even updated. It doesn't include the National Medal and another major award that he's won. So instead, I'll pick and choose. And I'll choose three, two of which you can probably guess. But before I do that, Barry grew up in Nebraska. He was born in Nebraska. He moved to Los Angeles when he was in grade school. And he was a product of all public schools, elementary school, high school. This is a famous, iconic that you've seen in many movies and stuff, Marshall High School. And then he went to UC Berkeley. He is his first in his family to go to college. He really had no role models. He had no idea what physics was. He discovered physics at UC Berkeley. He, before that, thought he wanted to be a tennis star. His only mentor that he's told me about was actually his tennis coach, who realized that all the other students would come to him and ask him homework questions. And he said, well, maybe instead of tennis, you should go on to college. Those are also my interests, so I put them up there. Tennis, so as a father, people ask, what's it like to grow up with a Nobel Prize winner? Well, he only won the Nobel Prize 5 years ago. We played tennis, the other game that he liked, and then I really played tournaments and stuff, was chess. This painting, by the way, is from my daughter. She's an artist, and this is part of a larger work that she's doing. And that's more of what he looked like when we grew up. So, okay, well, I'm going to choose three prizes. Might as well start with the Nobel Prize. It's pretty daunting. It says, for those who, during the preceding year, have conferred the greatest benefit to humankind. It's a bit grandiose, but actually, it's if you go through the prizes. They're awfully impressive. But usually they take some time to really assess the importance of the science. It don't happen immediately. This was awarded as fast as it could have been after the announcement of the discovery of the prize, signifying the importance of the achievement of the measurement, as well as it opening up a new view of the universe. This citation's already been read. This is from the National Medal of Science. We were all in Washington, D.C. in October. This picture, fun fact, was taken by my mom. She had a better seat than me. She was one seat in front. And I also got the scoop of the citation. I sent it to my chair because I took a photo of the program, and Iqbal put it in the newsletter like instantly. This is a very meaningful award. Of course, the Nobel is too. That's really the scientific achievement. This is a little broader because it's service to the U.S. science. It includes not only his contributions to science, which are extensive even before not considering the Nobel and laser, but also his service to science. He was on the National Science Board. That's a presidential appointee for 8 years. He was president of the APS, among many, many other things, and that medal also signifies that. One thing that I didn't say when I was talking about the Nobel and LIGO is that he started this when he was about my age. And all my colleagues and stuff, why is he doing this? There's just no way you're ever going to be able to make that measurement. Basically, you couldn't prove that it couldn't be done, so to him that was enough. And he charted out a course to develop the technology along with the apparatus. And it took nearly 25 years, but with a huge payoff. And that's a lesson on how you pursue the most important and fundamental science, where you also have to have a partnership to gain that support, which was all supported by the US government. The third thing I'd like to highlight that he's very proud of, much earlier, was the 2002 American Association of Physics Teachers Klopstad Memorial Award, which recognizes outstanding communication of the excitement of contemporary physics to the general public. You'll see that in his talk, but also the importance of education, teaching, that he's had throughout his career, going well beyond his own science, but communicating science to students of all ages. He joined UCR in 2018. There's with my mom, posing with Scotty. He's done everything asked of him. And by the way, that also includes Richard Schrock, who was hired at the same year as Barry, who's a Nobel Prize winning chemist, who was also an alumni. So when Barry came, it was very important for him to make a difference, and there are two pillars to that. One was creating a new course, talking about the frontiers of physics, always looking ahead, just like when we play chess, always looking, thinking the vision of the future, as well as forming a new experimental group with the support from the administration in the frontier areas between physics and astronomy and experimental areas. So with that, I'd like to introduce my dad. By the way, that's my correction. Someone else on campus doesn't call him Barry, I call him Dad. And
Okay, hello everyone. I'm going to, in the next half hour or so, take you on the adventure of discovery, tracing what it took, why, and what it took to discover gravitational waves. We've done a lot since then, and there's a lot in the future. We heard a lot about that in the earlier sessions today, but I'm going to try to give you a real sense of how this came about and what it took to succeed in the next half hour. By the way, that backwards. The picture on the left is actually figure 1 of our discovery paper, and it just looks like a bunch of squiggles to you, but it's the signature that we expected from gravitational waves. There's no curves drawn through anything there. It looks like it's supposed to just from data. The shakiness is because data is not perfect, and what's shown is, that I'll come back to, is the left scale, if you can read it, has a scale that says 10 to the minus 21. That's 21 zeros and a 1. So that's the scale of the actual measurement that we'll make, and I'm going to try to show you why and how we succeeded in kind of the simplest terms I can. So we'll start with Einstein and gravitational waves in a little bit, but first Sir Isaac Newton. So gravity, we all learned gravity, I don't know, in elementary school, where your teacher said, what happens when you jump up? And your answer was supposed to be the earth pulls you down. That's actually not the right answer. So as I go along, you'll see why, but Newton didn't quite have that one right. But he gave us a formula that satisfied our understanding of gravity as being a force between two objects that's proportional to the mass of each object, so you're attracted by the mass of each object, and inversely proportional to the square of the distance between them. The formula on the very right is a different formula for gravity that comes from Einstein, and I'm not going to explain that in words. It's just there to show you that Einstein wrote down an exact formula. So the first thing is theories, formulas, understanding of physics. Newton wrote the treatise in 1687 on gravity, the book called the Principia. He spent most of his career developing the understanding that enabled him to write that book, which was the book that described Newtonian gravity. That is the little explanation that we have here. And in order to do that, he had to see, he believed it went inversely as the square, like this says, but then he had to prove to himself and then to others that it actually described nature. And so the first really big puzzle was how to describe the orbit of the planets around the sun. And the orbit of planets around the sun is an elliptical orbit. And the problem of how you go from this formalization of what gravity is, inversely squared, to give an elliptical orbit is difficult, actually. And it requires calculus. But there was no calculus when Newton started, and that's why he developed the rules of calculus in the 16th century, and he spent most of his time developing this little explanation for gravity, proving that actually, or trying to prove, he was challenged to do this, that the orbit of planets comes out of this formula as an ellipse, as ellipses. And that wasn't quite enough. He wrote his book, but he felt and believed that to actually convince himself and his colleagues that this is the explanation and description of gravity, it should be able to predict something else other than planets around the Earth. And so he identified the problem as being, instead of orbits of planets around the Earth, that there's a famous comet called Halley's Comet, and that he should be able to predict the orbit that Halley's Comet would take, and it happened to be visible during the period he was finishing this work. And it was the fact that he could, that the orbit that it followed his equations, that convinced him that he had the right answer, and that he published the Principia. There's about 100 copies of the Principia still in the world. And one of them is in Pasadena at the Huntington Library. But there's other places where you can see the Principia in its original form. So other than that little story, there's a lesson there that's true, and that is all theory. You hear people talk about theories of physics. All theories are approximations. It's our best understanding of the explanation of the physical phenomenon we're trying to describe at that point. It's not an absolute answer that's ever wrong. I'm going to talk about a different theory, or consequences of a different theory. It doesn't mean that Newton's wrong. We basically have added to our understanding of gravity, and Einstein's theory is undoubtedly an approximation as well. So all theories of physics are basically approximations to describe the phenomenon that we're trying to describe. So in the case of Einstein, the language changes. It doesn't sound like the thing on the left that I talked about, where you can kind of just visualize that as we take two masses, the force between them goes inversely proportional to the square of the distance. This is a little bit more complex because we don't even know quite what it means. Space and time are unified into a four-dimensional space-time. So first, space-time, if you put it in Microsoft Word, will give you a little wavy line underneath. So they don't yet understand that it's one word. But basically, this is a four-dimensional concept, and that's very hard to visualize. So all the pictures that I show you are really difficult to visualize because we can visualize a three-dimensional world, while time is the fourth dimension here, and it's part of everything that happens. So I'll keep throwing that in, but my pictures will look like three-dimensional pictures. Okay, so anyway, Newton published this book. It became and is probably the most important physics book ever written. It was totally, the force has a proportionality. Not only is it proportional to the product of the masses over the square of the distance between them, but there's a constant that goes there. It took another 100 years before someone was able to determine what that constant is. And so by the middle of the 1700s, we knew that formula and even its magnitude. And that was Newton's theory. And it stood until Einstein came along, in its form, until Einstein came. In fact, there were many tests, but the first time that it was doubted was by this man, was when this man here came along. And that is in about, I think, 1820. People would take the orbits of the planets and measure them, and they should follow this elliptical form. And it was seen that the orbit of Uranus did not follow Newton's equations. It was different than Newton's equations. So one consequence of that could be that Newton was wrong. This guy, instead of thinking that it was wrong, actually felt that it was wrong because there was a planet that we hadn't seen yet. So he, what we would call in today's language, reverse engineered the problem and looked at the orbit that Uranus had and determined what was missing. And so he found basically a planet, or where there could be hypothesized a planet. And he then, he didn't get along very well with his colleagues in Paris. And so he knew a young astronomer in Berlin that he sent a letter to. He gave 5 days for the letter to get from Paris to Berlin. And he told the reader that the astronomer on the other end, that if he would follow his instructions and look up at the sky on whatever date that was at a certain place, he would find a planet. And in fact, the planet was given a name by this guy called Neptune. And that was the discovery of Neptune. So that meant Newton's theory was valid, actually up until the time of Einstein, except for one other problem. It was seen later in the 1850s or 60s that if you look carefully at the orbit of the planet Mercury, it also doesn't quite follow Newton's laws. It's very, very elliptical going around the sun. It's our planet closest to the sun, and it has this very, very elliptical orbit. And so Levernier reverse engineered the problem again, and he determined what the features had to be of a planet that would satisfy that. And he gave it a name, which was later used in television, called Vulcan, for the missing planet. And in the 1850s and 60s, there were several false discoveries of the planet Vulcan, which didn't stand up. They were wrong. So it turned out that that discrepancy outlived this guy and did exist at the time that Einstein came along. Some biographies of Einstein attribute this discrepancy in the orbit of Mercury to Einstein developing his new theory of gravity. I think that's not true at all. The real history of Einstein is that in 1905, he solved 4 of the most outstanding problems in physics in a matter of months. And we call that basically the year of miracles. And the American Physical Society celebrated Einstein not when he came out with the century after his general relativity, but rather the century after his year of miracles. And so that was 2005. Einstein, everybody will realize, as part of what he did in 1905 was E equals mc squared, which later ended up being misused, but also the theory of special relativity, which is what happens when objects go very fast. And that's high velocities. When velocities are near the speed of light, then we have to make some corrections. And we learn that and study it at undergraduates even in physics. What was missing is what happens not when you have accelerations, when you have velocities that are fast, but also accelerations. So Einstein wanted to put accelerations into the problem. If you have accelerations, that effectively is gravity. Gravity accelerates the particles that move down. And so he added accelerations. Took him 10 years having to learn new mathematics to solve the problem. But at that point, he solved it and came out with the theory of general relativity, which is what we're going to talk about a consequence of, in 1915. At that point, he was living in Berlin, and he presented his new theory to the Prussian Academy of Sciences, which is all the big shot Prussian scientists. And he showed, as part of his presentation, that basically the problem of Mercury was solved if you used his theory. So the orbit of Mercury was perfectly fine if you used his theory of gravity instead of Newton's theory of gravity. But as a practicing scientist, not just a physicist, we know that explaining something that wasn't explained before doesn't give you the right to have a whole new theory of physics or whatever the subject is you're in. So that's not enough. He has to predict something important that's new. And he did that in the same speech. So in the same speech where he showed that his theory of gravity would give the right answer for the orbit of Mercury around the sun, he also predicted something else. And that comes about from this equation that I showed at the beginning, and that is that space and time are mixed together 4-dimensionally, and a consequence of that is that an object that goes at high velocity near another object actually affects the space and time around it, and effectively doesn't just zoom past, but can bend. And so he predicted that light that would come past the sun would be bent by the sun. And so he devised an experiment, that is, look at something that just happened recently, a full eclipse of the sun. at a time when there's stars moving behind it, and then measure what happens to the apparent trajectory of those stars, and then you could see if they've bent or not, and he calculated how much they should be bent, and that was tested in 1919 and proved the theory gave the right answer for the bending of light, and it was the bending of light that made Einstein a household name. It hit all the newspapers. The concept that light bends was the kind of thing that made people take note, and Einstein became famous. Okay, back to our story, which is gravitational waves. It starts essentially the same time. So in 1915, he brought forward this new theory of gravity. It had the success of solving the problem of Mercury. It had the success of predicting something new, the bending of light. And the next year, that was 1915, in 1916, was working with his new theory of gravity. And it's very difficult theoretically to work with. But he conceived it, he wrote down equations in a certain way, I don't know what for, and found that the equations of gravity that he had, although the letters were different, looked exactly like the equations that we have in electricity and magnetism, the transmission of light. And so from that, he concluded that light has waves that had been proven in the 1880s. And therefore, he made the intuitive leap. He didn't prove anything, that gravity must also have waves. He could estimate that the waves had to be not very strong, and he did that. But otherwise, he wrote this little article, not many formulas, it's about less than 10 pages long, where he predicted or suggested, or I don't know what word to use, that there should be waves associated with gravity just like there are electromagnetic waves. That paper was not only very rigorous and not very good, but it had some mistakes in it. It had a mistake of a factor of 2 in the strength of gravitational waves. So if it wasn't fixed, we would have been in a mess because the strength is different than what we measured. But he wrote a second paper in 1919, and in the second paper, he not only fixed the factor of 2 error in the first paper. Being Einstein, he didn't refer to the fact that the factor of 2 was a mistake. He just went on and put it in the factor of 2. But he also, in the second paper, told us what the source would be to make gravitational waves. And electromagnetic waves had been observed for the first time in the 1880s by Hertz. And he basically took 2 charges and wiggled them and went in the next room and detected that there were a signal from them, and then moved toward and away from the source and saw that it was wave-like. And that was the proof of electromagnetic waves. So gravitational waves also have to have a source, and the source isn't just 2 charges like this, but it's what we call a quadrupole. So that's a particular shape that one expects to have in accelerations, and that would make gravitational waves. This whole subject kind of wasn't picked up very much because this is the era when quantum mechanics was coming to the fore. And so most of physics was concentrated on applying quantum mechanics to our understanding of the atom and so forth and so on. And there just wasn't much attention paid to the question of gravitational waves. Einstein picked up the question, though, again, in I showed you Mercury. That's Mercury's orbit around the sun. And this is just the idea that space and time are warped around an object, so around the Earth. Space and time are warped, and each point on this grid is a point in X, Y, Z, but also in time. So before we talk about gravitational waves a little more, there's 2 things that we now have a new theory of gravity. He showed he fixed the problem. And there were two problems really with Newton's theory that had to be fixed. One was a problem that Newton recognized in the Principia, and he wrote about it a little bit. There's at least a phrase or a paragraph, if I remember right, where he talked about the fact that basically when the apple drops and the observer looks at the apple, that the observer sees it in his theory instantly. And so technically, that's instantaneous action at a distance. Something happens at a distance and you know it immediately. We don't have any mechanism for that. Information has to travel somehow. And we know, for example, in this picture here, that if right now the sun were to disappear, it would take 8 minutes before we would know it here. And that's because it takes, at the speed of light, that long for the signal or the information to pass to us here on Earth. So that's one problem that Newton actually recognized but didn't fix. He just said it. The second problem is that, let me see, I'm kind of mixed up on my slides. Going forward instead of backwards, that's the trouble. So the second problem, I'll just say in words, I don't know if I have it on a slide, is that when we were all in school, as school kids, and our teacher said, what happens when you jump up? We're supposed to say gravity pulled us down to the Earth. And of course, that's not the way Einstein would have said it. And so basically, Einstein told us why the Earth pulls us down to the Earth. Newton didn't, and it's because of this curvature of space and time. So he solved the problems of Newton's theory as they were known, either by Newton or otherwise, and made the new prediction, the bending of light, which I just mentioned, which was seen in 1919. Like often happens in physics, the discovery of the bending of light has many consequences. And often we make a discovery and then it becomes, in the next generation, a tool for future things. And now in astronomy, this bending of light has become a commonly used tool to understand an object because of looking at the light and as it's bent, coming around the object you want to look at. So where I have here in the middle an object, it could be a black hole or something. We can study it by watching the light come from stars that are behind it. And this is just some examples. The top one is a typical example of light behind, say, a black hole or some object. And the bottom one is the most easiest to see example of the bending of light behind an object. It's called the Einstein cross. It's usually most easily seen from the southern hemisphere, and it doesn't take much magnification to see it, a small telescope, if you're looking in the right place. The next point I want to make before I come to gravitational waves and the detection is that even something as abstract and as difficult as Einstein's theory of general relativity can have applications. We often find that a new discovery we have has applications that have nothing to do with what we were looking for. We were trying to solve a problem in physics or chemistry or whatever the subject is. In this case, we all use every day Einstein's theory of general relativity because the GPS system needs it. The GPS system is based on a set of satellites that are going around, something like 24 of them. They're going at 14,000 kilometers an hour, roughly, and that's relativistic. So there has to be a correction made when you look at how long it took the light from you, from your iPhone, the signal to get there and come back to you. It makes a correction for the fact that the satellite has moved because it's going 14,000 kilometers an hour. And that's a special relativistic correction. If you calculate it for the satellites, it's something like 7 microseconds per day. That correction's made in the satellites themselves. But there's a second correction, which is from Einstein's general relativity. and that is because the satellites are high above the Earth, the amount of gravity is only about a quarter of what it is here on Earth. And so that also affects how long it takes for the signal to go from your iPhone to the satellite and back. And in fact, that correction is the opposite sign. It's 45 microseconds per day, the other direction. And so altogether, the GPS correction, which is made in the satellites, is 38 microseconds per day. If you didn't make that correction and you do a little calculation, you would stay on a typical road for about 2 minutes if you were following it, and before you'd go veer off the road. So we use general relativity and Einstein's equations, all of you, almost every day when you use your GPS system. Now, gravitational waves. So this is the little paper that Einstein wrote in 1916, and I talked about that already. And basically then, from that, this is the view pictorially of what the gravitational waves are. Each of those little mountains is something, a black hole, a neutron star, some sort of astronomical object that one is captured around the other, just like the Earth around the sun. It goes around, one goes around the other. In this picture, the two may be somewhat equal masses. That doesn't matter. But as they go around each other, because they're going around a circle, they radiate away energy, and that energy in Einstein's theory, and that energy is the form of gravitational waves. So what you're seeing in this picture is two objects going around each other, and as they go around, they radiate away some energy with the frequency, as you see, that goes out. That energy that's radiated away is not like electromagnetic radiation that I talked about, that's photons. It's in space and time itself. So somehow in space, that form is radiated and changing the shape of space and time itself. The easiest way in an analogy to think about it is think about walking up to a small pond of water and throwing a rock into the water. When the rock goes into the water, the rock itself goes to the bottom, so you've stimulated it. But the ripples are like waves, move out. There's nothing going with them. It's all just water going out. And so the water is like space in a sense. There's not photons going with it like electromagnetic radiation or anything else. It's just traveling. And in Einstein's theory, it travels at the same speed as light, so it travels at that speed. This theory of Einstein's remained controversial because no one could derive, not the theory, but the theory of gravitational waves did, because no one could derive that gravitational waves come directly out of the theory of general relativity until a few years after Einstein died. He died in the early 1950s, and in 1958 there finally was a meeting where a British scientist named Pirani actually derived it from the equations of general relativity. And at the same meeting was my Caltech colleague, Richard Feynman, who said, other than it being mathematical, that if gravitational waves really exist, they have to be able to do something. It's not just whether they exist in some equations that you can calculate. So he made a little, what we call Gedanken experiment on the spot at this meeting, saying that if you took a rod like this and put a couple of rings around it, like you see in the picture in the top, and then a gravitational wave came through, it would distort the rod in a way that the little rings around it would move back and forth. Moving back and forth, they rub against the rod and create friction. That's a transfer of energy. And so basically, that's the idea of what gravitational waves can do. So at that point, which is 1958, it became accepted that gravitational waves do come directly out of the theory of general relativity and that they do things. So basically, it then became an experimental problem. So it didn't take us 100 years to detect gravitational waves. It took more like 60 or something. It was first a theoretical problem for 40 years. This is what they'll do. So if I had a gravitational wave and it went through the board here, it would take a circle. If I had a circle of, I'll use a term, free masses. So imagine those as, masses of marbles or whatever they are, but free to move. And you put them in an exact circle, and a gravitational wave came through. It would change the circle into an ellipse. Then it would change it into a horizontal ellipse, where the frequency of the gravitational wave is how quickly it would go back and forth from a vertical ellipse like I've drawn here to a horizontal ellipse. So that's the picture like on the very bottom here. And that's all we try to do in LIGO in our experiment is build an apparatus that can see that we've changed the shape basically horizontally and vertically. And we use a technique that isn't invented for this experiment, but the way we use it is. And that is called interferometry. If you look at the picture on the top, the idea is pretty simple. You start with a laser. So we use lasers, which, by the way, Einstein didn't know about lasers, although he actually wrote down the theory that eventually developed lasers. And he indicated that the gravitational waves could never be detected. That was not wrong because he couldn't envision the technologies that we've developed since that time. But anyway, so the idea is you start with a laser, like shown in the picture here, and the laser here. The laser comes to a mirror that splits the beam in two directions. And if these two directions are exactly the same length, the light will go down this one and come back in the same amount of time as the light that comes this direction and comes back. And then you can take an experimental technique, invert the two signals, and they'll cancel each other. And that's basically our technique. They cancel each other normally unless something intervened and made one of these arms longer or shorter than the other. And that's what would happen if a gravitational wave came through, because a circle becomes a vertical ellipse and then a horizontal ellipse at the frequency of the gravitational wave. So that's basically what we tried to measure. And all we had to do is develop an instrument that looks like this that could do it very accurately. And so the idea of the instrument I kind of show in a little movie here, if this works. Oops, let me go back. Here we go. So you split the light in the two directions, they just cancel. Now you change the length in one arm compared to the other, and some light comes through to where we would have our detector, and that's the idea. This is showing it as waves, because light is waves. It comes through, comes back. These two waves will exactly cancel each other. If they, like this, one's going up when the other's going down, and our detector, which is over here on the right, doesn't see anything. But if one of them becomes a little longer than the other, they don't come back at exactly the same time. And then we see a signal. And that's basically the underlying technique that we use to detect gravitational waves. So we perfected the technique. I'll show you the key things that had to be done very precisely in a minute. But we went to the National Science Foundation. Luckily, the National Science Foundation is very much oriented at doing very fundamental science, so they agreed to do this. And we had built two detectors. Our collaboration that worked on this was two institutions, Caltech and MIT, who we worked together for more than 20 years to do it. These institutions are usually rivals of each other, but for this, we work together. But you'll notice that this is this way and this one's this way. My MIT colleagues had a favorite possible site for one of these to put in southern Maine, and we looked at somewhere in the Owens Valley in California. But we weren't allowed to tell the NSF where to put it. We could only tell them what are the criterion for a site. And in the end, politics intervened, and it rotated from this way to this way. And so we have one in Louisiana and one in the state of Washington. This is a picture of them. They're quite large. So this is 4 kilometers on a side. This is Louisiana, if you don't notice. Louisiana, and it's in the middle of a commercial pine forest, and we just have a little land in the middle, 4 kilometers long. Louisiana is very swampy, and in fact, the water table is just barely below the ground level. And so the way we build it was to build it up above the ground level. You can't quite see this in this, but this is 5 meters high. And in order to build the berm, to put it on top like you do a highway, we used a borrow pit to pick dirt on either side, and that immediately became filled with water, all kinds of fish, and even an alligator the first weeks that we were there. So that's the device. Once you make it, and this is about the only technical picture I'll show you, you want to know how well you can do and what limits you. So the picture here shows the frequency of the gravitational wave. The frequency of the gravitational wave that we can look at here on Earth in our detector is basically the same frequencies as we communicate with each other, what we call the audio band. The reason is that for the same reasons that we've developed ears to communicate with each other and hearing, the ability to hear, is that's where the Earth is the quietest. And so the Earth is quiet means it's not shaking. If we tried to communicate with each other at lower frequencies, the Earth is shaking too much and we wouldn't hear each other. And if you go to too high a frequency, you can't sample quickly enough. So basically, we're limited to what frequencies we can look at, which is the audio band, kind of 10 hertz to 10,000 hertz. What I show here is where we're sensitive, and I'll explain. This steep line here is basically the shaking of the Earth. It happens to drop as the 4th power of the frequency, so that if we can live out here, it doesn't mean we can live over here. It went up too fast. This is the limitation due to how much light you have going back and forth in the interferometer. And this is just due to the fact that we use our instrument at room temperature. Someday we'll make it cold, but at room temperature. So the shaded area is where we can make detections. And I'll go back to that first detection you saw later. But this goes from a few tens of hertz up to thousands of hertz. So that's where we can detect gravitational waves if we can make it sensitive enough. So we started to use it. You can see that the shape is a little different scale, but the shape of the shaded area here is similar to the shape of what I show here. The different colors are subsequent years and improving the detector. So the highest ones are when we were least sensitive. We'd run the device, take data, try to look for gravitational waves, couldn't find any, improve the device, and then it goes down to the next level, and finally got down to the bottom, which was as good as we could do until we made some specific improvements that we had done a lot of R&D to develop, and we did those in the period between 2012 and 2015 when we made the observation. So basically, we improved the interferometry, which is indicated here, where we go from a simplest kind of interferometer like that movie to a very complex one, which I won't describe. And so we could improve the interferometry, which we've done. But the interesting thing is that's not all that limited us. The other limitation is shown here, and that is that we're limited by the shaking of the Earth. And it turns out that we have to reduce the shaking of the Earth by 1 part in 10 to the 12th of what the real shaking is. And that is done by a pretty simple idea, but hard to implement. And that is we use the same technique that you use in cars. So in a car, when you drive, in the early cars, if they went over a bump, you'd bump up and down as you sat in the car. But then we developed shock absorbers. And what a shock absorber does is it takes the fact that you hit a bump, which is high frequency, and it transfers that to much lower frequency, and you just feel a very gentle motion as you go over a bump, if the car has good shock absorbers. So in our case, we had to make the world's best shock absorbers. And so we designed shock absorbers that were much, much better than you have in your car, and we made 4 different layers of it. One set of shock absorbers, and if any shaking got through those, we had a 2nd layer, 3rd layer, and a 4th layer. We did all that, and we still weren't good enough to detect gravitational waves. So that was maybe 2011, 2012. So we had one more, not exactly trick, but one more way to make us more sensitive, less sensitive to the motion of the Earth, and that is to use, again, a technique which we're familiar with, but a different application. And that is when we go on and fly an airplane, we've all used some version of mine are Bose earphones that you put on, and they measure the ambient motion of noise from the engines and cancel it electronically. And if a stewardess comes in, so you don't hear it anymore, it's very gentle. And if a stewardess comes up to you, you still hear the stewardess ask you whether you want coffee, tea, or milk, because that's not an ambient noise, it's a shake, and so it doesn't get canceled. So we do the same thing with seismic noise. Well, we have this big device that's getting rid with shock absorbers to get rid of the seismic noise. We can't do the same thing as really the same idea, but the same thing that's done in Bose earphones. So here what we do is bury inside of our array of shock absorbers seismometers that measure any residual motion of the Earth. And we also put little actuators in that can push and cancel that motion. And that gave us the final factor that we needed to detect gravitational waves. So what we expect, and then I'll show you the signal, is something like this. If you look at 2 binary objects going around each other, then the sketch on the left shows what happens. They may be spinning, which is shown here, but as they go around each other, they'll get closer and closer together and eventually merge. So they have some up and down shape, then they merge. And then after they merge, there's a settling down period at the very end. So this is the typical signal. How many cycles up and so forth depends on the masses of these 2 objects, how far apart they are, and so forth and so on. And we can calculate all that, and we get the signal that we want. And this is the first signal that you saw. And as I said, it was the main figure in our discovery paper. The second figure in the discovery paper is even more revealing to me as an experimental physicist. What's shown here is the same pictures as these. One of them's here, and one of them's here. And they're shaky a little bit because that's how well we measure things. It's just how well our instrument works. The second line, the second pane along here is smooth curves. It looks a lot like these, but they're smooth curves. That's directly the calculations from general relativity and Einstein's equations that fit this data. And so that's what we use to interpret it, which I'll show you in a minute. And then, as just an observer or an experimentalist, what you do is subtract this from this, and you get this pane here. This is the most revealing. So as an experimentalist, if this is the same as this is just the random noise of how well we did the measurement. If there's some shape, then there's something we're missing. The fact that this doesn't do anything but shake up and down means that this is just has some errors on it, but it's measuring the same curves as this. And so that was the data for the discovery. We can then use Einstein's general relativity to calculate what the objects were. And that's done here. So what we calculated is that there were two objects. One was 36 times the mass of our sun. The other one, 29 times the mass of our sun. And the final object is 62 times the mass of our sun. You'll notice that 36 plus 29 is not 62, it's 65. The reason for that is that the equivalent of 3 masses of our sun went away in the form of gravitational waves. So the initial objects, if you weighed them, were 36 times the mass of our sun and 29 times the mass of our sun, and the final object 62 times, and the equivalent of 3 times the mass of our sun. That much energy went away in the form of gravitational waves. And if you could measure it as just where the most energy was in the universe at that moment, it was the brightest object in the universe at that moment. So I'm going to show you one more observation, and then we'll call it a day. Soon after, the next year, just actually after we received notice that we were going to receive the Nobel Prize, we made another observation. And that observation is shown here. Basically, by that time, a third gravitational wave detector built by a French-Italian collaboration was also not quite as sensitive as us, but able to observe. And so we saw an event, and we're able, by triangulation, just like you do on a ship or something, to tell where you are, to tell where it happened in the universe. And this is where it was. And it happened that at the same time, a satellite that measured very high energy gamma radiation saw a signal coming from the same place in the sky. This is their location in the sky. This is our location in the sky. And they both were the same. The picture over here on the left shows all of this. The very bottom is our signal. This is time and frequency. The frequency goes up as we get to the merger, and it happens at exactly this time. I project that up through these lines here. This is the observations of the gamma ray satellite, and you'll see they see a peak here, and a peak here, and a peak here, just a little after, about a second or so after we see ours. That object, we were able to identify what galaxy it was in, and how far away, therefore how far away it is. And that object that merged and made this signal was 150 million light years away. 150 million light years is 1.5 10 to the 15 seconds. And so since these signals are within a couple seconds of each other, that is immediately an observation that gravitational waves and light waves traveled at the same speed to basically 1 part in 10 to the 15. Amazing. And that's just from that simple observation. The next thing, this is just more on making that observation, which I've said. Since we saw it at the same time, we were able to immediately announce this where to look in the sky to astronomical instruments around the world. There's a way to communicate with, astronomers communicate with each other. And so we announced that we see this merger. We knew, by the way, I'm not talking about it in detail, that this was not black holes. It was two what are called neutron stars merging. I won't go into why, but it doesn't matter very much. This immediately alerted astronomers around the world, and it was the biggest mobilization of astronomical instruments ever. something like 2,000 astronomical instruments proceeded to look at that place in the sky and saw the signal. And that signal was traced for days and weeks, starting with it giving the high energy gamma rays that we saw, then giving lower frequency light in different colors, eventually giving things like X-rays, and finally radio signals, which come last a couple weeks later. And so following that whole parade basically enables the people that analyze the data to use modeling to determine what happened when the neutron stars came together to give this signal. And there's a rather good model of that, and it fit very well. So this is just the data. And the interesting thing is that this solves, we think, it's only one observation, a problem that existed since I was a graduate student. So physicists like to try to explain everything in nature, whether we know the answer or not. It's all right, we'll correct it and get a better answer later. And in this case, I recall at the time I was a graduate student in Berkeley, there was an explanation for, there's a question, and then how do you get the answer? The question is, how did the heavy elements get into the Earth when the Earth was formed? When the Earth was formed, if it was just cosmic rays and so forth, if it's just light, there's just light elements. The only way we get heavy elements is in the burning of the sun. The burning of the sun uses the fusion process, which was talked about a little earlier today. And that process starts by having the same fusion reaction that created the hydrogen bomb, basically, starts with the light elements. So mostly when a star is burning, it's burning hydrogen, lithium, helium, eventually oxygen, and so forth. And it works its way up to heavier and heavier elements. But the fusion process, which is a well-known physics process, only really works up to iron. You can't go to heavier elements than iron. So this process doesn't explain how gold or platinum, our favorite heavy elements, got into the Earth. So the explanation has always been that it's an enhanced nuclear process, something that always had the label the R process, which is a nuclear process. But now you can model it as two neutron stars coming together and how much gold was produced in this collision that we looked at. Clearly the collision we looked at has nothing to do with what got into the Earth, but a similar collision could have, or similar ones, happened at some earlier time. And the one that we saw, we can calculate from just the calculations produced 100 Earth masses of gold, just this one collision. So you can imagine now, although we've only seen one event like this, that the best explanation we have for how the heavy elements got into the Earth was not the fusion process in the sun, but the collision of two objects like neutron stars, like we've seen. So that's how science moves forward. We had some earlier talks today on how there's it's as difficult as it was to make LIGO, we have a fairly well understood path for how to improve it. And we've been doing that. So we've basically improved it, and the number of events that we have observed has gone from these first time where we had 400 days before we saw more than 2 or 3, to now seeing some sort of gravitational wave event every other day. And if you come and ask me, I'll give you the app you can download that'll tell you every time one came in. So with that, I've given you a quick tour of the discovery of gravitational waves and some of the obstacles and so forth that it took to do it. Thank you.
Well, thanks, Barry, for a fantastic presentation tonight. That was phenomenal. Do you have time to answer perhaps
Sure, of
two
course,
questions?
of course.
So Thanks to everyone in the audience who have presented some questions, but due to some time limitations, we're just going to ask two. The first is, what is your advice to aspiring physics majors in developing their own interests?
Well, of course you want to pick interesting problems, but I think you shouldn't, physics is hard. If you want to do something like physics because you like physics, it should be fun. So one thing is to intellectually ask what are the interesting topics, analyze where we're going to make breakthroughs or possibly breakthroughs. But then when you look at what it takes to do it, it should be what intrigues you and what you want to spend your energy on. And you can't be afraid of failure. I think as a physicist, to try to do something like this, we fail and fail and fail and fail and then finally succeed. Sorry.
So the second question is, what do you think are some of the ways that we can promote physics and sciences to minorities and young kids in general?
Yeah, that's a great question. I wish I had a really sharp answer to that. I think we've gotten much better than we used to at sharing the advances in science with the public. We're still not great at it, but we're getting better and better than when I was a student. To really solve the problem, we have to solve it at a young age. We have to get young kids, whether they're minority kids, women that we don't get enough of in science, or any other kid to get interested in science at a young age. And I think the problem then is really teaching at a very young age. I believe we have, I'll just make one anecdote. Kids are curious. If you take a kid of 5 or 6 or 7 years old, they ask a zillion questions and their parents say, shut up after a while. And their teachers say, do your work. And actually, and we even have a saying, we say, which is a terrible saying, saying curiosity killed the cat. Well, I think people who have been successful in science like myself somehow escaped all that. We shouldn't have to escape it. Curiosity is a wonderful feature, and I think the driving force of doing science. And so not only exposing kids at a young age to science in as creative a way as we can, but to the adventure of discovery, that they should be curious, and so forth. It's just built into the heart of it, and there's no reason it shouldn't be kind of built into the way we introduce kids into whether it's hard science or just things that challenge you in life at a very young age. And curiosity may have killed the cat, but it's what we need to do great science.
Okay, it's been a very long day. We started these celebrations at around 11 o'clock this morning, and Barry, as the person being rightly celebrated, has been going all the time since then. I'd like to thank the faculty and the staff of the Physics and Astronomy Department for imagining this event, for helping to put it together. I'd like to thank all the staff from the college for helping as physics and the Dean's office started to plan and then execute these events. On behalf of the college and of the university, a very heartfelt, sincere thanks to all of you for coming out this evening to hear this extremely interesting presentation by Barry on gravitational waves, and a big thanks to Barry for everything you've done for science in the United States and the world, and for what you're bringing to UC Riverside at the current time and in the future, and all the best for the centre that's been established here on gravitational waves and experimental cosmology.
Well, thank you, and thanks for the support for this event.
Okay, thank you. Safe travels home, everybody, and thanks again for coming out this evening.